I think I'm back. Sorry, I connected to a different internet yesterday because I was talking to someone and there was an internet issue, and apparently that's the one that's volatile. I know the one that's not volatile I should connect to, but it was not connected to, and now we're back to being non-volatile. Apologies for that. Let's go back to the learning. We're back.
This is basically, you can do this anytime you're doing reinforcement learning by just training a regression model that does this for you based on the rewards you get. The important thing is the baseline is not allowed to use any of your actual predictions, because once you start using the predictions, then it's not a baseline anymore. Another option, which is relatively easy to implement but can still be effective, is you calculate the mean of the rewards in a batch. And so if you have a big batch of data and your average reward in the batch is like 0.4, then you just subtract that 0.4 and calculate your reward based on that. So that's another option that you can use.
Okay. I will say I don't know how to use any of the things he said, and yes. Yeah. Like I cannot imagine them. So yeah. It sort of went over my head is what I'm saying. Looks like I'm still 30 seconds behind based on what I sent message. Oh, really? Huh, why? There is no dropped frame rate. Well, maybe you can just refresh, it's fine.
A kind of extreme example of this, of creating a baseline, is contrasting pairwise examples, or contrasting different outputs for the same input. And you can easily learn directly from pairwise human preferences, which can provide more stability because you know one is better than the other. So you essentially can be sure that you're upweighting a better one and downweighting a worse one. This is the idea behind DPO, which is a recently pretty popular model, but there's also other previous methods that did similar things. And the way DPO works is it basically calculates this ratio of the probability of the new model to the old model, but it upweights this probability for a good output and it downweights this probability for a bad output. And so
okay.
Here we have our better outputs over here. Here we have our worse outputs. And it's basically learning to upweight the probability and downweight the probability accordingly. So you can notice that DPO is very similar to PPO in that it's using these ratios, but the disadvantage of this is you obviously require pairwise judgments and you can't learn a model if you don't have these pairwise judgments. So. Yeah, so the beta term is basically a normalization term. It's a hyperparameter. For DPO, sorry, I read the paper right when it came out, and I don't remember if it's a direct derivation from the KL divergence term or not, but I think it might be. I'd have to go back and look at the paper. But basically, the larger this is, the larger gradient steps you'll be taking. It also like you'll notice there, sorry, I didn't mention this, but you'll notice there's a sigmoid term here.
Mm-hmm.
So the beta, the larger you increase the beta, the more small differences in these values, like it basically like stretches or shrinks the sigmoid with respect to how beefy it is. So it will affect how much like small differences in this will affect your gradients. But I think this was derived from the KL regularization term that we had previously in this slide here, but I'd have to go back and double check unless somebody knows. So it is? Okay, good. Yeah. So, I don't want to say wrong things, but I also don't want to. Okay, cool. And so then increasing batch size, because another thing is kind of necessarily reinforcement learning is going to have higher variance and maximum likelihood estimation just because we're doing sampling and other things like
higher variance and maximum likelihood sampling. Okay.
this. And so one very simple thing you can do is just increase the number of examples or rollouts that you do before an update to stabilize. And so I would definitely suggest that if you're seeing any stability after doing all of the tricks that I mentioned before, that you increase your batch size, and often that can just resolve your problems. Another thing that people often do is save many previous rollouts, because generally doing rollouts is more expensive. Doing rollouts and collecting rewards.
DPO is very important for ChatGPT, really. ChatGPT special also has Verbit, unless I'm misremembering. DPO. Direct or something? Oh, why did I forget what it stood for?
This is more expensive. And so you can save the rollouts that you have done before and keep them around so you can update parameters with larger batches in a more efficient way. Cool. So that's all I have. I just realized we're exactly at time, so I should finish up here, but I'll be happy to take any questions up front for people. Thanks.
Nice. I will continue the learning because we just came back. Yeah, next lecture that is about debugging and interpretation, which is like on the other side of training. Well, maybe in like in the middle. Yeah, debugging and interpretation. Okay. Start.
So in my slides here, I'm going to talk about debugging and understanding NLP models. And this is how to tell when, for example, both your implementations are wrong and, for example, your underlying assumptions are wrong, or your model is failing on particular segments of data or stuff like that. So I'm going to go through a variety of things that can go wrong with your experiments, basically.
Okay, I like that.
So a typical situation is you've implemented some NLP system, based on neural networks, of course, because that's what we use nowadays. And you've looked at the code, it basically looks okay, but it has low accuracy or it makes incomprehensible errors. And you would like to fix these, or you'd like to improve the accuracy or something like that. And so what do I do? And I think there's 3 dimensions of how you can understand your model and your model behavior. The first one is debugging the implementation. So it's identifying problems that you have when you implemented something. Second thing is actionable evaluation. So identifying typical error cases and what you can do to fix them. And finally, interpreting predictions or interpreting what's happening inside the model. And this can maybe give you a deeper idea about what's happening in individual cases. And there's a lot of reasons why you might want to do that. Both like to make your models better, and also, for example, if you want to be sure that your prediction isn't doing something illegal, like discriminating against people due to protected attributes or other things like that. So there's a number of reasons why you'd want to do that. So I'm going to talk about the first 2, and Nishant is mainly going to talk about the second one. So going right into it. So in neural network models, debugging is really important because they're opaque, they're unpredictable, and if you make little mistakes, they can cause big problems with your output. And another thing is that everything is a hyperparameter, including your network size, your model variations, your batch size, your strategy, your optimizer, and your learning rate. And finally, unlike kind of more traditional machine learning methods like logistic regression or support vector machines or something like that you might have studied in your machine learning class, stochastic optimization has no guarantees about convergence. Your loss might go down, then it might go up, and there might be absolutely nothing wrong with your training, or it might be, a serious problem. So that's another issue you need to deal with. So first, I'd like to go into possible causes of problems with your implementation.
We're starting with training time problems. My question is, when do we start looking into our data being not good, or do we assume our data is great?
And I'm going to break them down into a typology, and based on what part of the typology you're running into problems with, you will need to fix them in different ways. So your first goal when you're experiencing the problem is identifying why you're experiencing the problem, because that will lead you to a solution. So for training time problems, there's a bunch of things that could be wrong. The first is a lack of model capacity. So your model is not able to model the phenomena that you want to model in the first place. You could have a poor training algorithm. You could just have a bug in your code at training time. Another thing is test time problems, and these can include a disconnect between what you're doing at training time and what you're testing at testing time. Failure of search algorithms. And another thing you'll want to deal with is overfitting. So you're actually doing well on the training set, but you're doing poorly on the test set. Finally, you could have optimize a mismatch between the function you're optimizing at evaluation time and what you're actually evaluating. Sorry, the function that you're optimizing at training time and what you're actually evaluating at test time. And my best piece of advice for figuring out why things are going wrong is don't try to do all of them at once, and rather start from the top and work it down, because the ones at the top are often easier to diagnose than the ones at the bottom.
Okay.
So
there was like a discussion about testing and training, but I don't know if they were related to data, more to what we're doing with the data.
Looking at how you can debug systems at training time, there's a number of ways you can do this, but the most important thing for training time issues is looking at the loss function calculated on the training set. And what I mean by this is, don't look, we talked about how we can't optimize error or accuracy easily, so instead we optimize likelihood. And so you might want to look at accuracy to see whether your model is working well, but I would urge you first to look at your likelihood or your loss function on the training set instead of your accuracy on the test set, for example, to diagnose these variety of problems. And the sorts of things you want to look at are, is the loss function going down? So is it, converging into a good place? In general, if this is your loss, the first thing you should—
So we just look at the graph, like visually?
know is like, what is a good loss? In most cases, a good loss is zero. Like log likelihood, the best loss you can achieve is zero. So you have zero down here. Something like this is essentially a good loss function. Something like that, especially if this is a relatively high number, is usually a bad loss function. Something like that on your training set is a very bad loss function. Something is going seriously wrong. If you see this on your dev set, that could be, or your test set, that could be overfitting. But if you're seeing that on your training set, that's usually symptomatic of a problem. So these are things that you should be knowing. Is it going down basically to zero if you run training long enough for many epochs over your training data? So if it's not going down to zero and it's sticking up here, then that's also an issue. And if it's not going down to close to zero on whatever training set you're training on, let's say you make your training set extremely small, at least in that case, it should go down to zero. Otherwise, you might have a serious problem in your implementation. So these are good things to check first when you're training a model. And there's a number.
It should go down to zero, but that doesn't mean it should get to zero, right? Because that would be overfitting, like you just said. Or no?
Reasons why this might not be helping, or why this might not be happening. So your model might be too weak. And so in general, larger models tend to perform better, especially if you're using a pre-trained model. And this is just an example from the T5 paper where they scale up the T5 model from a relatively small model to
Huge.
what at the time was a very large model of 11 billion parameters. Now this is, moderately sized model or maybe even small model by some standards. But anyway, you can see that it continues to increase. One really interesting phenomenon is that actually larger models can learn faster, or at least with fewer steps than smaller models. And so this is an interesting example. This paper on neural scaling it's a very influential paper, but basically what they show is the darker purple ones are smaller models. The yellow ones are bigger models. And what you can see here is the purple model, and on the left side, they have the number of tokens processed. On the right side, they have the number of compute, or the amount of compute. And so what you can see is if you just look at the number of tokens processed, the larger the model, the faster it converges, which is maybe a little bit surprising, maybe a little bit, or maybe like some people have the intuition that this should be the case. But when I first saw this, I found it a little bit surprising because I thought it would be so large and noisy that the model would have trouble fitting the data as quickly. But there's actually a good reason for this. Does anyone have a guess about why this is the case?
Isn't it just more relative to the smaller model?
A little bit about the underlying phenomena for this in previous classes, so you might be able to think back to some of the things you've seen. Yeah. Yeah, so just to repeat, there's a lot of different parameters, so it can try to converge along a lot of different dimensions. So if we think back to the model pruning class and other stuff like that, part of the reason why we can prune large models so efficiently is because only a small number of the parameters are actually useful. And so if you start out with a much larger model, it's more likely to have useful subsets of the parameters, basically, which is called the lottery ticket hypothesis. There's a famous paper called the lottery ticket hypothesis that examines this phenomenon. So one interesting thing is you can see that even if you scale up the compute, even if you measure based on compute, the larger models eventually surpass the smaller models in terms of how efficient they are at modeling the data. And that's just because models tend to learn well for a while, and then they basically reach their capacity and stop learning well, or they start learning very slowly. And once you get to that point, the larger models work better. So there's a kind of counterintuitive thing that if you want to train faster, you actually can train a larger model, and that will get you to a good solution. At some point, that will get you to a good solution faster than a smaller model would. Of course, you need memory and stuff. Right?
That is very counterintuitive.
Are you punching on a different data set? Isn't that training?
So this is test loss. Training loss also looks like this. I think on this particular paper, they never repeated data. And if you never repeat data, actually your training loss looks very similar to your test loss. Because if you can assume your training data set and your test data set are identically distributed, your training loss of new training data should be exactly the same as your test loss. So they were justified in doing that here. But they probably did test loss to assuage the concern that this was overfitting to the training data or something. But good question. Cool. So these are good things to know. So basically, if you see your model doing something like this, plateauing out, maybe your model's too small and you need to train a bigger model, basically.
Okay.
Another piece of trouble that you can have is trouble with optimization. And basically, you should check your optimizer. Usually people are using atom variants nowadays, like atom or atom W, so just use that. Learning rate, so make sure that the learning rate you're using is standard for kind of the model size that you're using.
I still haven't grasped learning rate. But I know that people say, this is a good one to use. I'm like, okay, I trust you. Using decay.
The best way to do this is look at previous papers and see what they're using. initialization, most people nowadays will not be training from scratch, but if you are training from scratch, how you initialize your model is really important. And normally the way you do this is you do this with some sort of uniform random noise. And specifically, you can pick the uniform random noise in intelligent ways based on the data size, which I'll talk about in a second. Also, mini batching. Are you using sufficiently large batches of data? If you're using small batches of data, you might have too much noise in your training and it might diverge. So these are things you need to think about as well. Cool. So these are training time things. The next thing is debugging at test time.
Let me see. Oh. Sort of want to stop here actually. Because I think it will take. So he said 3 things: training time, test time, and the other thing that no, it was actually a few more. Wait, 12:37. Wait, test. 1, 2, 3, 4, 5. Yeah, 5. No, 4. Okay. Training, test, overfitting, and mismatch between optimize function and eval. Hey, I just saw that. Right. Yeah. Okay. Okay, I can do 5 more minutes. Right? Evaluation. So this is how we find the problem and then what we do about it, sort of.
And this is particularly important if you're doing any.
I think it's learning rate, like step size, ignoring the effect of momentum. So it's hard to predict what will work without going empirically from trying to train a bunch of models and seeing what effect different values have. Okay. Yeah. It's basically like this is what other people have used and this is what have worked for them.
Any sort of like, I guess a lot of this has kind of been commoditized and it's implemented in HuggingFace and stuff like that. And as long as you're using the standard implementations, you're less likely to run into these bugs. But if you are implementing anything on your own, this is actually really tricky and you can easily make mistakes. So it's important to know about it. So
It did actually. Like comparing it to step size does help.
One of the reasons why you can have training and test disconnects, especially if you're doing something like text generation, is that usually your loss calculation and prediction functions will be implemented in different functions. And like anything in software engineering, this can be a source of bugs. Duplicated source code can be a source of bugs because you might implement one thing in one place in one way, another thing in another place in another way. So this is no exception to that. It's especially true for structured prediction models. So anything where you're not just making a single prediction, but you're making multiple predictions in a row. So you need to be a little bit careful about that. Another thing that you need to pay attention about is often, especially if you're doing your own implementation, loss calculation is mini batched and generation is not, or in highly optimized versions of inference, you might be doing inference with dynamic batching and stuff like that, and it might become complicated and you might make mistakes. So how do we make sure that we're not making any mistakes here? There's a really simple way to debug any sort of mini batched loss calculation, because normally when we mini batch loss calculations, we're simultaneously calculating the loss for like 4 or 8 or whatever sequences at a time. And so you can calculate the loss with a large batch size like 32. and then calculate the loss for each sentence individually and sum them together. And these values should be the same. And this can help make sure that you don't have any, issues with your padding or your masking or other things like this. So this is particularly important if you're not just using out of the box things, like you have a slightly unusually structured model with like hierarchical encoding or anything like that. You need to be really careful about that. You can even create unit tests that test this. So like in machine learning code, we don't write unit tests, or especially neural network-based machine learning code, we don't write unit tests that often because it's kind of hard to do. There's lots of randomness and other stuff like that. But this is one thing that you can easily test and make sure that you don't have any mistakes in.
Okay.
Any sort of generation algorithm. So when you're generating or decoding, you can make sure that your decoding code is getting the same score as when you calculate the loss. And an easy way to do this is you call the decoding function to generate an output. And normally when you're doing any sort of search or sampling or something like that, during the search or sampling, you're calculating the logits or the log probabilities of each step that you sample. So you keep track of that during your sampling algorithm. And then after that, you call the loss function on the generated output, and you calculate the loss according to the loss function. And the score of these two things should be the same. You do your generate, and that gives you an output and score. And then you do loss on the output.
Okay.
And that gives you score 2. And then you just compare these two things together. And this can, in my experience, this has allowed me to find the majority of the bugs in these two things. Have allowed me to find the majority of the bugs whenever I was doing any sort of like complex thing with respect to generation or models and stuff like that. So
oh, that's why. So, okay, now that makes sense. Why we're comparing these two is because we want to find the bug. Ah.
Thing with respect to generation or models and stuff like that. So it's a very common place for bugs, even if you're pretty familiar with models. So I would highly recommend that. This is particularly bad when you're doing something like a search algorithm, like beam search. And so beam search, as you know from the generation class, instead of picking one high probability, word in your next step, you maintain several paths. And one way that you can fix this is as you make search better, the model score should get better. So the log likelihood of the output should get better almost all of the time. So you can search with varying beam sizes and make sure that you get a better overall model score at the end. So, and you can even create a unit test testing this as well. I don't think that many people will be re-implementing beam search, so you might not need to worry about that too much. But in case you are doing anything with respect to search algorithms, it's a good thing to know.
Okay.
Cool. Any questions about these two so far? No? Okay.
Okay. Cool. I think it would be interesting if we just like, I feel like I want to be spoon-fed, but if there were like examples, because I like working with examples more. But if I go to the class, I don't think in the assignments, like there are, 2, 3, report. How many assignments were there? I thought there was just assignment 1 and 2. 4 assignments. 4 assignments. I thought, wait, has it changed? Oh my god, rag. I think this has changed. Because I thought build your own llama was assignment number 2. It says spring 2024, so it's not updated by a lot. I am actually interested in this. It looks like so much work. Someday. Additional resources. Tutorial on... Wait, what is that? Tutorial? It was in the past. And not recorded. Probably. Only the Q&A session seems to be... No, not recorded. Let's be optimistic and Google it and hope that it was recorded. It is. 4 hours. Please let there be voice. University, what is that? Of Washington? No, help.
Sorry. Yeah. Sorry. I have no idea.
Imagine this class would have... probably tutorials we don't have access to. You mean like, what is it called? Something where the assistant lecturers help you. Yeah. They expand on the lectures with practical stuff, help with assignments. You are right about that, yeah. When does it start? Okay, 10 minutes in, nothing.
And spend the next 3 hours with all of you on this group of fantastic speakers.
Really? The audio is recorded from the room? That's just cruel. Oh, thanks. Someone says it starts here.
With a huge student progress. Okay, so next, please let me talk a bit about how we can organize the part today and how we hope that we can participate in the part. So first of all, we have already put all our slides and also the reading list on this
I mean,
website.
I can listen, but not well. At least I know it's here. I'm gonna copy the link. Wait, no. Did I copy the link? I don't know. Copy the link. Wow. It's supposed to be from 2 to 5:30. Wow. Okay. I'm gonna continue here, but they tried, yeah, trying to record tutorials well above standard, even for open courses. This is supposed to be from ACL, so like, wow. I think I will still go through it on my own another time, but I doubt I'll watch the whole 4 hours. We'll see. Starts at 18 something. Yeah. We'll see. Okay. Still, I'm happy that it exists and it's from almost a year ago. So I don't know. Most of the time with these things, you never know if anything is updated. I'm gonna have to fix this. Anyway, if anything is updated to the point where the information is no longer relevant or if things are just the same.
Hi, I'm Taylor and welcome to Crash Course Linguistics. Spelling can be a mess. Take the letter. Hi,
sorry.
I'm Taylor and welcome to Crash Course Linguistics. Spelling can be a mess.
Speak for yourself. My language is doing fine for a second. I'm bad at spelling.
Take the letters O-U-G-H. They're pronounced differently in tough, cough, though, through, bow, and brought. The letters don't always match the sounds they represent. What's more, people can pronounce the same words in different ways. There's a difference between I am going to get you and I'm gonna get ya. If we want to talk about the different ways people can pronounce the same spellings or which sounds exist in different languages, it's useful to have a more precise understanding of how language sounds work. The study of speech sounds is called phonetics, and the writing system that linguists use to write pronunciation very precisely is called the International Phonetic Alphabet.
Phonetics. Okay, really? Sound, study of sound. Ah, okay.
Speech sounds don't include coughing, sneezing, or belching. They're the sounds that spoken languages combine with each other to make words. While there are a finite number of speech sounds, we can use them to make an infinite number of words. To understand speech sounds, we first need to understand how the human body produces them. We start with the lungs, which push air up through the vocal folds, also known as the vocal cords. Your vocal folds are thin membranes that sit across your throat and vibrate to make sound. This path, which moves from lungs to lips, is known as the vocal tract. We can change the shape of any part of the vocal tract to make or articulate different sounds. It's like a wind instrument. When air goes through it, it makes a sound. You're like a squishy, wet meat clarinet that can articulate sounds. I'm sure that's an image you'll never forget. For spoken languages, the tongue, mouth, and the rest of the vocal tract are the articulators, the parts of the body that move to make language. For signed languages, the articulators are the hands, face, and other visible parts of the body. There are 5 major features of signed language articulation. Hand shape, such as the difference between the ASL sign for red and sweet. Palm orientation, such as the difference between balance with the palms down and maybe with the palms up. Movement, such as moving in a circle for always or a line for scold. Location, like mother at the chin or father at the forehead. And expression, also called non-manual signs, like furrowed eyebrows to make something a yes or no question. There are some conventions for writing signed languages down, but there is less consensus about how to write them than with spoken languages. Describing all these systems in detail would be a whole nother video.
Like writing sign language down, I'm curious if, like, because we write what we say, but not how we say it. I mean, unless it's a novel. We don't write emotion in text. Like, you write and then you add emojis.
Spoken language linguists also describe sounds in relation to how they're made with the articulators. Consonants are speech sounds made by closing the vocal tract in some way, while vowels are made by making it a different shape but leaving it open. We'll look more closely at vowels in the next episode. To dive into how linguists write spoken languages down, let's start with some consonant sounds you know, which happen to be some of the most common sounds in languages across the world. P, T, and K. Try making these yourself, and pay attention to what your mouth is doing. P, T, K. These sounds all require you to close off part of the vocal tract to make air stop before you let it explode.
I do sometimes. American was making the point. Yes, that's the point. Got it. Yeah, just to show that I'm non-threatening. I also do that quite a lot. Yeah. P is in the front, T is somewhere in the middle, and K is like all the way back, right?
Explode out. which is why they're known as stops or plosives. These 3 sounds are made at 3 different spots in the vocal tract, which linguists call places of articulation. We often name these places according to the parts of the vocal tract used to make the sound. So since p is made by pressing both of your lips together, it's a bilabial sound. T is made by pressing the front part of the tongue against the hard ridge just behind your teeth, known as your alveolum, so it's an alveolar sound. Some people also call the alveolum the pizza ridge, because that's where you burn your mouth when you take a nice big bite of a hot slice. And k is made by pressing
Only a pizza?
the back of the tongue against the soft part of the roof of your mouth, known as your velum, so it's a velar sound. We can put these sounds on a diagram of a mouth to show these different places of articulation. The square brackets here indicate that they're phonetic sounds, not English letters. Let's look at 2 more sounds we recognize, f and s. Unlike our stops, these involve the air continuously flowing out of and causing friction in the mouth. So this type of sound is a fricative. F is made using the bottom lip and top teeth. That makes f a labiodental sound. S is pronounced at the alveolar ridge, just like t. This means s and t have the same place of articulation, but they're different in their manner of articulation, because t is plosive and s is fricative. K has a corresponding fricative too, h. It's not in most varieties of English, but it's the sound in the Scottish loch or the Spanish jalapeno. Now try this with me. Put your hand on your neck.
I have a note about ch, because jalapeno, or is it, my question is it he or is it ch? Because they come from the same place, sort of. One includes vibration, one doesn't. I feel like the way she said it, she mixed the 2, which is okay. But yeah, cool. I like this.
And make the sound s, and then turn it into a z. Your lips and tongue stay in the same position. You're not changing the place or manner of articulation, but something does happen in your throat. For s, your vocal cords aren't vibrating, while for z, they are. Seriously, try it. The buzzing of your vocal cords is also known as voicing.
Oh.
S is a voiceless sound, and Z is a voiced sound. Each of these sounds we've discussed so far has a near identical voiced twin, like F and V, P and B, or T and D. Even the velar fricative H has one. It's found in many languages, including Arabic, Basque, and Navajo, and is written with this curly Y symbol based on the Greek letter gamma. To continue our tour of the vocal tract, another manner of articulation.
This is supposed to be r, right? Ch and r? No? Right? I need to know. I can't make the latter sound. I don't think we have that in English. The ch one? It's alright.
Is nasal sounds. We make them by closing the mouth but opening the nasal passage using the velum. In English, we have m, which goes with our bilabials p and b, and we have n, too, which goes with our alveolars t and d. We also have the nasal sound at the end of sing and in the middle of hunger, which goes with our velars k and k. We normally write this ng sound with an n and a g, but that's not useful for phonetics because some ng words like hanger don't have the ng sound. Ing needs its own symbol, so we use
Ing is like Koreans have the ng sound.
this little n with a tail stolen from a g called an engma. In fact, the word engma has a velar nasal in it. How convenient. Our mouth diagram is beginning to look a little cluttered. We have our places of articulation, which move from left to right as we move further back into the vocal tract. We can treat these like columns in a table. Now we can make different manners of articulation into rows. Great, this chart is such an improvement. We know it's based on the mouth, but it's a lot easier to read. Because it's hard to make a chart in 3 dimensions, we'll represent voicing by placing the symbols in pairs inside the boxes, where the first symbol is always voiceless And where there's only one symbol by itself, it's always voiced. We could keep going by paying attention to what the mouth is doing as we pronounce different sounds in English and other languages until we have a comprehensive table of possible speech sounds. For example, there are a ton of other manners of articulation. We could add approximants like trills like the R in Spanish perro, and taps or flaps like the T in butter. There are also lateral fricatives, like
I literally did not notice that R is not on this diagram.
the Welsh pronunciation of the name
Nor, oh wow. Nor is L, because R and L also are twin letters. Go back, go back, go back. Why isn't it going back? Oh, okay, it is now. There we go.
lateral fricatives, like the Welsh pronunciation of the name Llewellyn, and lateral approximants, like the English pronunciation of Llewellyn. There are also more sounds that we haven't gotten to, especially in other places of the vocal tract, which get constricted in various manners. But let's take a step back from the examples for now. It turns out this table we've been building is a chart of the International Phonetic Alphabet, also known as the IPA. The IPA is a finite set of symbols used by linguists to represent all of the sounds that are relevant for a spoken language. Let's head to the thought bubble to find out more about the IPA. The International Phonetic Alphabet was created in the late 1800s by a group of linguists who were tired of putting a pronunciation key at the beginning of every document. If we could just make one system where each sound had exactly one symbol, they thought, then people could learn it just once. Then we'd be able to write about all the sounds relevant to spoken languages without any confusion. Unlike attempts to write down all the words in the world, which end up going on forever since we keep inventing new ones, this project actually succeeded. There are only a finite number of ways that we can configure our mouths and throats to make sounds, and only some of those are used in languages. The phoneticians who started the IPA were mostly from England and France, so they created symbols using Latin and Greek alphabets, which they were familiar with. And it comes before the days before computers, so many of the symbols are rotated versions of existing letters. That way, they wouldn't need to go forge a whole new set of letter forms or create a new kind of typewriter just to explain how to pronounce gavagai or something. Occasionally, a new symbol gets added, such as the voiced labiodental flap in 2005. But for the most part, we've figured it out. Thanks, Thought Bubble. The IPA chart is a bit like the periodic table in that its structure tells us a lot about the properties of each sound. This means that even if you don't know a symbol immediately, you can figure out what it sounds like based on its row and column. Or you can look.
I've watched this video once before, and we'll talk about it in a bit, but I like this chart because there are things that humans cannot or cannot pronounce.
Up a clickable IPA chart where you can click on each symbol and hear it pronounced. I've tried it. It's pretty fun. The empty white boxes are sounds that could exist but haven't been found in any known language yet, while the shaded gray boxes are sounds that we just don't think the human body is capable of making. There are also two categories of other consonants that don't fit in the consonant table the way it's commonly structured. The first are sounds where the articulators touch in two places, called co-articulated consonants. They don't easily fit into any one column in the table. For example, w not only involves the lips coming together, but also a constriction at the velum towards the back of your mouth. The second are consonants that aren't made with air flowing out of the lung, or pulmonic airflow, so they're known as non-pulmonic consonants. This category includes sounds where the air is sucked into the vocal tract, or implosive consonants, and sounds where the glottis is sealed up and air is forced out of the upper part of the vocal tract, known as ejectives. The final group of non-pulmonic consonants are clicks. You make a dental click sound when you make a disapproving. Some languages like Zulu and Xhosa and the Khoisan languages include click sounds in the standard set of consonants used to make words. And that's how linguists represent all the consonants. Whew! The International Phonetic Alphabet was crucial before it was easy to make and share recordings of language. It's for this reason that opera singers, speech pathologists, and accent coaches all find it useful to work with the IPA. Now that recording digital sound is everywhere, the IPA helps us teach computers how to recognize and copy human speech. The IPA is also great for helping you understand new speech sounds you encounter when you start learning a new language. Unlike reading something in standardized English spelling, reading something in IPA is an intimate experience. You're reading it back in exactly the accent of a specific person. But so far, we've actually only talked about half the IPA, the consonant half. In the next video, we'll look at vowels. Thanks for watching this episode of Crash Course Linguistics, which is produced by Complexly and PBS. Are you craving more humanities in your YouTube diet? Then head over to Storied, PBS's home for the liberal arts geek in all of us. Storied features Monstrum, a show about monsters and myths and what these stories say about us. As we gear up for Halloween, Monstrum's host and writer Dr. Z is going on a deep dive of zombies, tracing their evolution from Haitian folklore to the brain-eating creatures we know and love today. Subscribe to Story.
Huh, this was in October 2020. Huh. That's cool.
For Monstrum and other great shows, and tell them Crash Course sent you.
Nice.
Hi.
Cool. Nice. Okay. So yeah, I shall try to run this sometime in the week. And like I think I can give it 3 to 4 hours of like me being next to the computer and seeing where that goes. And if we fail, it's okay, we shall continue. But I'd like to have something. I'm sure that other people have tried it, so I can train it based on what other people have done. But for now, I still want to try my own one more time and then give up. Giving up is always an option, so I can do that as well. I think that's all the energy I have for today. I do feel like yeah, a bit with like lack of energy past week, so let's not force ourselves to learn more, because learning uses brain power. There we go. Can we add checkpoints? Huh. But checkpoints are resume on a checkpoint. That's actually a good one, but normally checkpoints are with epochs, right? Not steps, and it's only one epoch. It's like pretty small. I'm gonna like take that into account. It must be a part of the training argument, right? I'll think about that. Checkpoints. Okay. I'm gonna write what is the thing a person writes? Note. There we go. Can we add checkpoints? Question mark. There we go. Okay. Will do. Thank you. Yes, weekend is still a little bit left, so I'm gonna enjoy what's left of it. And I started a course recently, so I think it's like probably like a full year course. We'll see. It's based on how long it will take me to finish it. So I'm looking forward to starting that. So wish me luck on that. And yeah. Have a nice weekend as well. Inshallah, things go well. And even if they don't, hope we learn from them. Okay. I'm gonna end the stream. If there's anything else, let me know. Otherwise, see you next time. Ending in 5. Oh, what's happening to my eyes? 5, 4, 3, 2, and 1. Thank you. Bye.